All right, we're going to finish chapter 5 now. So, if the idea of induction is somewhat counterintuitive, the idea of strong induction is, well, it's a bit weird. What I'll say is that strong induction is really no different from regular induction, except that we're going to make a slightly different subtle point, right? Now, in, let's say, the normal induction, we have our basis, right? Which is just to show that P of, we'll call it 0, is true. And then we suppose, right, and then with our induction, with the inductive step, right, we suppose, right, well, actually, we have this thing, right? We have if P of K now, what are we going to do now? The book kind of makes a bit of a thing. Well, for the basis, right, I'm going to show that P of 0, right, and P of 1 up to some P of B, I'm going to call it, right? I'm going to show that these are all true. And then in most cases, you're only going to really need to show that one or two things is true. But this is sort of a general form, right? If I had to show that 10 things were true and actually, in order to actually meet what I needed to in my inductive step, then I would actually do that. And I'm going to give you a slightly different example than what's in the book to talk about why it's important to have strong induction. Sometimes regular induction might not work that well. So for most things that we can do with just regular induction, we could do with strong induction, right? So this is a slight difference, is that I actually have to show multiple things in my basis. And so then what do? Well, let's assume that we're proving it for all in, right? So for the inductive step, now normally we would suppose that P of K is true for some value K. We're going to do it a little bit different. What I'm going to do is I'm going to say for all, basically I'm going to say for all values I between 0 and K, right? That P of I is true, right? And it's going to be the same type of thing where if that's true, then I'm going to deduce that P of K plus 1 is true. Right? So, I mean, like we could prove anything that we've done so far, right, the same way. We could prove the stuff from 5.2. We could prove the stuff from 5.3. And you can look at the examples that are in 5.4. The examples are pretty good in 5.4. But I'd actually like to show you a time that they're actually kind of it's kind of necessary for me to actually use this in practice, right? When do I need really more than one? When do I need to have proven more than one thing in my basis step, and when do I really need to use this assumption that it holds for everything? I'm gonna take a brief diversion into something called recurrence relations, or recursively defined sequences. So you can have sequences, right? So if you've taken calculus or something, maybe you remember the idea of a sequence. So I could have something like A0, and then I have some A1, I have some A2, and then so on, right? Well, sometimes we have sort of like, well, how do I get the numbers in this sequence? Well, you know, maybe it could be from a series, or maybe it could be from some other things. And there's actually a kind of interesting way I can define sequences, and that's recursively. And I'm going to show you a kind of interesting recursively defined sequence, right? There's a really famous recursively defined sequence, the Fibonacci numbers, right? So 1, 1, 2, 3, 5, right? 8. So you notice that the, let's call this the nth, is just the sum of the previous two, right? So this number 2, that's the sum of this one and this one. Then the number 3 here, that's the sum of 2 and 1. This 5 is the sum of 2 and 3, and so on. Right. That's a fairly famous. Now we often need these sort of like base cases, initial conditions. A lot of recursively defined sequences are very similar, or the recurrence relations are very similar to, if you've ever taken differential equations, you often have a differential equation, and you have to have, if you want to have specific solutions to a differential equation, then you need what are called initial conditions. So let me define a recursively defined sequence. Right. So I'm going to say that an is a n minus 1 plus 2 a n minus 2. And I'm going to have a0, right, equal 1, and I'm going to have a1 be 5, right? So since I have the n minus 1 and the n minus 2, I actually have to have a 0 and 1 initial condition term, and to actually get specific solutions, right, to this. Now, I could find different terms of this iteratively, right, or recursively, really. I could, you know, if I wanted to find the 5th term in the sequence, well, I'd have to know that I'd have to start kind of working my way back up, right, from the very bottom, right? I'd need to find, well, I have to go to the 0 in the 1st term, and then I have to go to the 2nd term, and then when I know the 2nd term, I can get to the 3rd term. When I get to the 3rd term, I can get to the 4th. When I have the 4th term, I can then finally get to the 5th term, right? And so sometimes something we like to do is have, instead of having them defined recursively, we might want what's called like a closed form solution, right? So this is I'm going to claim. So I claim that an, right, the nth term in the sequence is equal to 2 n plus 1 plus negative 1 to the power of n plus 1. Right. So let's see, right? If I want to prove, right, this is my claim. I won't go into actually how I found this. There's a particular way of finding solutions to these what are called first order linear recurrence relations. And once again, if you've taken differential equations, it's very similar to finding solutions to some first order linear differential equations. But I'm not going to go into the method I used to actually solve this. But this is a thing that I'm claiming is the case. Now, if someone gives me this, I might actually want to prove that that's correct. I might want to prove the correctness of the closed form solution. So how could I prove that this is correct? Well, I could use induction, right? And in fact, I need to use strong induction to prove this. Right, so let's see how the proof works, right? Proof. Right? This proof is by induction. So let's start with the basis. Now notice that if this is my basis, I want to prove that it's true for P of 0 and, right, for P of 1, right? Because look, I have two initial condition things that have to be satisfied. So, right, so first for P of 0, so first we'll do P of 0. Now when n is 0, right, notice that the sort of left-hand side, my A0, right, is 1, right? So the left-hand side is just 1. And then my right-hand side is, right, remember I'm claiming it's this thing, so that's 2 to the 0 plus 1 plus negative 1 to the power of 0 plus 1. Right, and so that's equal to 2 minus 1, so that's just 1. So the left-hand side and the right-hand side are equal, so P of 0 is true. Right, now next for P of 1, I have that my right-hand side is just equal to 5. And what's the left-hand side? The left-hand side is equal to 2 to the power of, in this case, this is 1. 1 plus 1 plus, I've got negative 1 to the power of 1 plus 1. So that's 2 to the power 2, that's 4. That's negative 1 to the power 2, that's a positive 1. So this is equal to 5, right? So again, the left-hand side and right-hand side are equal. So I know that for sure, right, that both of those basis steps are satisfied, right? Now for the inductive step, right? Now inductive step. Now for this, remember, suppose basically for all i's, for all values of I, I guess it's from 0 because it's, in started at 0 there for our index. So from 0, so I between 0 and k, right, I want to suppose that P of I is true. Right. Now, if we would need a reminder of what that means for some value I, right, my ith value of the sequence is just 2 to the power of I plus 1 plus negative 1 to the power of I plus 1. Okay? All right. Now consider the k plus 1 elements. Well, I don't know what it's equal to, but I do actually know from the sequence itself, right, from the recursively defined sequence, that ak plus 1 is just ak plus 2 times, right, this is 2 times ak minus 1. Now look, I know that this is actually equal to something, and by our sort of strong induction, I know that this can actually be equal to something too, right? Before, what I'll say is that it's not really something we could do. I really can't say that right before, because we only assumed it was true for some value of k, and we were sort of using that to sort of build ourselves up to the k plus 1. But in this case, I'm assuming that any value of I between 0 and k, it works, right? And basically the lowest I can go down is to 0 and 1, right? And I know that those are true, so, you know, for any values in there, I'm assuming it's true, right? So the kind of nice thing I can do here is say that ak plus 1 is equal to this, and then just do substitution. I know that this is actually going to be equal to 2 to the k plus 1, right? Plus negative 1 to the k plus 1 power. Then plus 2 times, this is 2 to the power k plus, ooh, my goodness, plus negative 1 to the power of k. So I'm going to do a couple of things. Some things are going to look really weird for a second, and I'll explain what I'm going to do. So I've got 2k plus 1. If I distribute this all the way through, I actually have another 2k plus 1. So I'm going to group it over here, 2k plus 1 together. Now I have a plus negative 1 to k plus 1. And then I've got plus 2 here. This is 2. This is 2. And then if I multiply that through, I've got 2 times negative k. Or I'm sorry, negative 1 to the power of k. I guess I didn't need that extra thing over there. My bad. Okay. So if I do this and this, this is 2 times 2k plus 1, so actually something very nice happens to me. So this is 2 to the k plus 2 power. Hopefully you can see how that worked, right? This is 2k plus 1 plus 2k plus 1, so that's 2 times 2k plus 1. If I have 2, right, so 2 times 2k plus 1. Really, if I'm multiplying 2k plus 1 by 2, I can really think of that as 2 to the power 1. And when I multiply, I add exponents. So now, what would be really nice is if I could get, because I have sort of the first thing I want, right? I have this 2 to the k plus 2. This is really 2 to the k plus 1, right? That's really what I want to have there. So it would be really nice if I could get negative 1 to the k plus 2 power. And we can actually do a little bit of this. So something interesting here. What I'm going to do is I'm going to pretend that this is actually, so this -1 to the k plus 1, I'm going to sort of break this apart, and I'm going to say this is actually -1 times -1 to the k plus 2 times -1 to the k. So this is just some algebra stuff. And notice here, what I'm going to get, right, is that this is 2 to the power of k plus 2. And if I do -1 times -1 to the k plus 2 times -1 to the k, well, this is just going to cancel out and just give me plus -1 to the power of k. Now, really what I want is I want this in the form of -1 to the k plus 2. And there are a couple of ways we can think about this. One way to think about this is that I'm multiplying this by a +1, right? And this is actually something I can do, right? This is 2 to the k plus 2. Well, another way of thinking of +1 is actually of -1 squared, right? -1 to the k. And now notice this actually gives me what I want, 2 to the k plus 2, plus this is -1 to the k plus 2. So there it is, right? And notice in this case, we really needed that extra layer in strong induction. Now, like I said, you can still use strong induction for any of the other stuff that we've done so far. In either regular induction, we could still prove it using strong induction, but sometimes that might be a bit overkill. So I think really strong induction lends itself quite well to instances where we need to fill in the gaps in between. Like when I really need to know that, you know, if I'm at k, if I go below to k minus 1, I'm guaranteed to have something down there that's true, right? Okay.